Okay, so the title is Conjectures and Counterexamples. Now I realize those are both new words. We'll start with looking at conjectures, and then counterexamples comes up toward the end of the lesson. So I just want you to focus on right now that a conjecture is an educated guess based on a pattern. So for example, if I have a pattern like 2, 4, 6, and then it continues on, my conjecture might be, okay, they're adding 2 to get to each term. That would be my educated guess. So we're going to be looking at patterns and making conjectures about what's to come based on those patterns. Okay, so the warm-up is use the pattern shown to make predictions and complete each statement. What's nice is they kind of like started the statement already, and this is what they're hoping for. It says the square of an odd number is an even or odd number. So what we're going to do is look at the pattern. So it says use the pattern to make a prediction about whether the square of an odd number is an even or an odd number. So here, squaring an odd number, we get an odd number. Squaring an odd number, odd number. So it looks like every single time it's coming out to an odd number. So our conjecture, our educated guess based on the pattern, is that it always comes out to an odd number. Our conjecture may be wrong, but based on this, that's what we can determine. Next, it says the square of an even number is an even or odd number. So we look, when they square an even number, they get an even number. Squaring an even number, it comes out to an even, and it keeps coming out to an even. So our conjecture here is that the square of an even number comes out to an even number. So all of these are going to be conjectures. Educated guesses based on a pattern. And then this one, the sum of an odd number and an even number is a blank number. So we have an even and an odd. It comes out to an odd. Odd and even, it keeps coming out to an odd number. So our conjecture is the sum of an odd and an even number is an odd number. Okay, this one, a little bit different. They switched up the style of the problem. It says the product of any number in 10 is a number that ends in what? Well, if we multiply this by 10, this number ends in 0. 13 times 10, it ends in a 0. Okay, so if we multiply a number by 10, the answer always ends in a 0. This example, okay, we'll do it. I was going to skip it, but we'll do it. So here it's saying you have 12. It wants to know if this is divisible by 3. So one way to determine this, and you may have seen this in math before, is if you add 1 plus 2 and it equals a number that's also divisible by 3, then 12 can be divided by 3. So 12, 1 plus 2 is 3, and 3 is divisible by 3, so therefore 12 is divisible by 3. If you want to know if 24 is divisible by 3, you can add 2 plus 4, and if 6 is divisible by 3, then 24 is also divisible by 3. Same with 36. You can add 3 plus 6, you get 9. If 9 can be divided by 3, so is 36. And here it's showing, okay, 132. You can add 1 plus 3 plus 2. We get the number 6. If that's divisible by 3, then the whole thing is. So if the sum of the digits of the number are divisible by 3, then the original number is divisible by 3. So what we're doing is a process called inductive reasoning. Inductive reasoning. Inductive reasoning is a process of reaching a conclusion based on a pattern of examples. When you assume that the observed pattern will continue, you are applying inductive reasoning. We use this a lot in real life. For example, if it took you... Yes, we use inductive reasoning. We look at patterns in real life a lot to predict predictions about the future. You can use inductive reasoning to make an educated guess Based on known information and specific examples, this educated guess is known as a conjecture, which is what we're doing. Okay, so now we're going to look at some examples. Example 1 says, write a conjecture that describes the pattern in the sequence. Then use your conjecture to find the next term in the sequence. So here it says appointment times are at 8:30, 9:15, 10 a.m., 10:45. So we're looking for a pattern here. I noticed that every appointment comes 45 minutes later. So like plus 45 minutes, and then the next appointment. Plus 45 minutes, the next appointment. Plus 45, the next appointment. So our conjecture is that appointments are scheduled 45 minutes after the previous one. Based on the pattern. And it wants us to find the next term or terms in the sequence. Well, based on this, 10:45 plus 45 minutes would be 11:30, plus another 45 minutes, 12:15 p.m., and so on. We could continue. Aiden, can you take your AirPod out, please? Is he good? Oh, you getting a calculator? Oh, that's smart. Shanice, have you? Oh, you got a calculator. Cool. Okay. Erica and Alex, did you get a calculator? Oh, you can get a calculator. I don't know why. Okay, perfect. Okay. Next one, it says write a conjecture that describes the pattern in the sequence, then use your conjecture to find the next term in the sequence. Okay, so looking at this sequence here, 1/2 to 1, so that would be times 2. 1 to 2, they're timesing by 2. 2 to 4, they're multiplying by 2. So, my conjecture, the next number is 2 times the previous number. So if I was to fill in the next numbers in this term, 4 times 2 would be 8, 8 times 2, 16, 32. So okay. And over here, there's a couple examples. We're going to cross out this one and just do this one. It says, make a conjecture about the sum of two odd numbers. So in this case, they didn't show us what they're talking about. So what we have to do is make some examples. Make a conjecture about the sum of two odd numbers. So I'll just try out some examples, like 1 plus 3, the sum of two odd numbers, or 5 plus 7, or 9 plus 11. And I'm making some examples of adding two odd numbers to see what happens. So I get 4, and I get 12, and I get 20. Okay, it looks like the sum of two odd numbers always equals an even number. So my conjecture, the sum of two odd numbers equals an even number. Okay, in the examples, it says example 3 and 4, we're going to look at more like real life examples, which is where this usually comes up. We look at trends and numbers to make predictions about different things. This is a hot topic right now, gas prices, of course. It says the table shows the average price of gasoline in the United States for the years 2010 through 2018. Make a conjecture about the prices of gas in 2019. Explain how this conjecture is supported by the data given. So here it shows 2010 to 2018. We're going to make a prediction about 2019 and what that gas price is. Okay, so based on this chart, I'm going to look at whether it's increasing or decreasing, or what years it's increasing or decreasing. Let's see, from here to here, 284 to 368, it's increasing. So it's going up. And then it starts going down again, and it goes down all the way to 2015, decreasing. Did I get, yeah, it's decreasing. Oh, it actually decreases all the way to 2016. Okay, 2016 is decreasing. Then it starts increasing again. So increasing. And it looks like it's increasing for about 3 to 4 years. It decreases for about 3 to 4 years, increasing, and so on. So 2019, I would guess that it's increasing. So my conjecture is that it would continue increase. In 2019, the price of gas will continue increasing. And I could explain this data, but I already showed it, so I feel like that's good. Okay. Next example, another real life example. This business owner is opening up an ice cream shop and collected data on the total sales for the first 5 months. Make a conjecture about the sales total in 6 months. Explain how your conjecture is supported by data. Okay, so we have this chart. Month 6, we're trying to figure out what the predicted sales would be. Okay, so I'm looking at patterns here. From month 1 to month 2, increased $200. Then from month 2 to month 3, it goes up $250. Then here it goes up $300. Okay, so I'm seeing a pattern here. It's going up $50 each month. And then we got up $350. And then my prediction is that in month 6, it would raise $400. So I would get $2,000 in sales. So my conjecture is that month 6, the sales in month 6 will be $2,000 based on this pattern. Okay, in this little excerpt here, it seems small. I might actually have you write some of this a little bit bigger. To show that a conjecture is true for all, okay, show that a conjecture is true for all cases, you must prove it. It only takes one example that contradicts the conjecture, to show that a conjecture is not always true. This example is called a counterexample. So this is that word that I said we were going to bring in toward the end of the lesson, counterexample. And it can be a number, a drawing, or a statement. And then we're going to flip to the next page, and we just have a couple examples on the next page. Okay, so over on this page, we're going to talk about counterexamples. Over here, example 5. So now we're going to bring in counterexamples. A counterexample is an example that disproves a theory. An example that disproves a theory or a conjecture. Just put that in. So we made our educated guess, but what if our educated guess is wrong? A counterexample would prove that it's wrong. Zoom in here so you can see the example. Okay, so here it says find a counterexample, so an example that disproves the statement to show that each conjecture is false. So here it says if n is a real number, then negative n is a negative number. Well, if n is a real number, so if n equals 4, then negative 4 is a negative. It works there. But we're looking for a counterexample where that doesn't work. So what happens if, use my example that I used earlier. Right. Oh, how'd you get that? Okay, so our counterexample, so like when this wouldn't work would be if n is negative 4, which is a real number, then negative n would be negative 4, which is positive, which is a positive number. Okay, so for B, it says if angle ABC and DBE are congruent, then ABC and DBE are vertical angles. Well, they could be vertical angles to be congruent, but they could be congruent without being vertical angles. So a counterexample to this would be, okay, you have angle ABC and angle DBE. They're not vertical angles, but they're both, let's say, 46 degrees. So that means they're both congruent, but they're not vertical angles. So here we say angle ABC is congruent to angle DBE, but they aren't vertical angles. Okay, so then here they bring up the challenge level a little bit. They say find a counterexample to show that each conjecture is false. Select all that apply. So here it's saying if n is a real number, then 1 over n is less than n. So we're looking for things that are false. So I'm actually going to start with the true ones, which are D and E. So D and E are going to be true. We can plug in 5 for n, and we'll get 1 over 5 is less than 5. Okay, that makes sense. 1/5 is less than 5. That is true. Then here, for 100, 1 over 100 is less than 100. And I'm just plugging it in for n. Okay, that works too. That's true. But we're looking for the false statements that prove that this doesn't work. So over here, 1 over negative 3, is that less than negative 3? Negative 1/3 would actually be greater than negative 3. So this is false. So this is a counterexample. Then here, plugging in 1/4 for n, 1 over 1/4, is that less than 1/4? Well, 1 divided by 1/4 would just be 4, and that is not less than that, so that is false. So this would be a counterexample. And then here for 1, if I was to plug in 1 over 1, is that less than 1? No, 1 is not less than 1. That's false. This is a counterexample as well. And then this one, we're looking for a counterexample again. It says if a line intersects a segment at its midpoint, if a line intersects a segment at its midpoint, then the line is perpendicular to the segment. No, it doesn't have to be. So this is not 90 degrees. Therefore, it's not perpendicular, but it's still bisecting that segment. So this would be a counterexample. That a line can still bisect a segment without it being 90 degrees. Okay, and that's us all. So your to-do list to do homework 3-1 on Schoology, and then work on Alex. And if you have like all 10 Alex's done, which I don't know if anybody in here has all 10 done, you can ask to get your phone, but this is your to-do list. So grab a computer, get your homework done, and I'll turn